Hello students, welcome to today's lesson where we are going to look at production of X-rays and X-ray tube. We start with X-ray tube. Now X-rays are produced when fast moving electrons are suddenly stopped by a matter, and this happens inside the X-ray tube. Now these X-rays can pass through most substances including the soft tissues of a body, but not through bones and most metals. Maybe you have ever gone to a hospital with a fractured bone and you are put under the X-ray photo. What you see is that you are able to see through that photo, you are able to see the part of the bone that is broken because that X-ray is able to pass through the flesh of your bone or the flesh of your tissues, and it is stopped by the bones. These X-rays are produced by modified discharge tube that we call X-ray tube. Inside that X-ray tube, we have the cathode that is in form of filament, and this cathode is the one that emits electron when it is heated. The anode is made up of solid copper, molybdenum, and we call it target. And we are going to see that it is made up of copper because it is a very good conductor of heat, so that when it gets heated, that heat can be dissipated or it can be conducted away at a faster rate. A higher potential difference between the anode and the cathode is maintained by an external source. Then the filament is made up of tungsten and it is highly coiled to ensure that it provides a high resistance to the current. And when it provides this high resistance, then it will be heated faster. And when it is heated faster, then it will give us more electrons at a faster rate. The tube is highly evacuated so that the electrons do not collide with air particles. If they collide, they will lose some of the kinetic energy. The X-ray tube is surrounded by lead, and this will help us to absorb any stray X-rays. Then from there, we move to the diagram of X-ray tube. As you can see, we have our focusing cathode, we have the filament, this is our anode, and we have the target. We have the cooling fin, we have the cooling fins here, and then we have oil in and oil out. This one also enhances cooling. Then this glass tube is highly evacuated. The inside here is a vacuum, so that now these electrons do not collide with any other particle. So when this one is heated, it produces electron or it emits electron, as we are going to see in production of X-rays. Now when a cathode is heated, it produces electrons by thermionic emission. The word thermionic is coming from the word thermo, and thermo means heat. So it implies that the electrons are being emitted due to heat energy. And what happens is that when they are heated, they gain a lot of kinetic energy, and that kinetic energy is enough for them to detach themselves from their atoms. So when they are emitted, they are accelerated towards the anode by the high potential difference between the cathode and the anode, and that is approximately 100 kilovolts. So that way they are able to go to the anode, and where we have the anode is where we have the target. Now when the fast moving electrons are stopped by the anode, that is our target, part of the kinetic energy is converted to X-rays, and the other part is converted to heat energy. That is why our target becomes heated when this one is in use. Cathode is concave shaped, as you can see, and this will help to focus electron beam to the target. The cathode is coated with oxides of low work function, and this will ensure that electrons are easily emitted. When we talk of work function, this is the amount or the minimum amount of energy required to dislodge an electron from the metal surface. So it implies that if it has low work function, the electrons will be dislodged easily. That is why now we are saying the oxides are coating the cathode, because this cathode is the one that is giving us what? Electrons. Then from there, we have that the anode target has a high melting point. Remember, we have seen that most of the kinetic energy is converted to heat. So this anode gets heated, so it has to be cooled. But before we start cooling, it has to be made of a material of high melting point. And the material that we use is tungsten or molybdenum. Now, most of kinetic energy of electron is converted to heat energy, but only about 0.5% is transferred to X-ray radiation. So you can see that about 99.5% is converted to heat energy. So therefore, it is important to know that anode has to be cooled. And anode is made up of good conductor. And this will ensure that we have a fast dissipation of heat energy. And also we have the oil circulation and the cooling fins. This will enhance the cooling process. We have also a lead shielding that has a high density, and this will prevent the X-rays from penetrating into undesirable targets. Remember, we talked of lead absorbing any stray X-ray. Then from there, if we want to get the power rating of X-ray, we always get the applied potential, we multiply by electron beam current. So in other words, the rate of energy conversion is potential difference multiplied by the current. In modern X-rays, you find that the target is made to rotate, and this will help us to change the point of impact, thus reducing the wear and tear. Then the target is set at an angle of 45 degrees, and this is done so that we can direct the X-rays out of the tube as shown here. You can be able to see that we have the filament that is being heated from the external source of heat or source of current. Then we have evacuated tube, we have the rotating anode, we have the lead shield, we have, this is our motor that is rotating our anode. So this angle is 45, so that when they hit, or the electrons hit the target, then we can be able to direct the X-rays outside the tube. And this one is rotating to change the point of impact, thus reducing the wear and tear. After that, we move to energy changes in X-ray tube. When the cathode is heated, we have seen that the electrons are emitted through the muonic emission. When they are emitted, they acquire what we call electrical energy. And this is given by EV, where E is the electron charge and V is the accelerating potential. This one is a constant, and its value is 1.6 times 10 to the negative 19 coulombs, as we are going to see later. Once in motion, remember now they have been emitted, once they are accelerated, this electrical energy is converted to kinetic energy. And from previous topics in Form 3, we know that kinetic energy is calculated by a half mv squared, where m is the mass and v is the velocity. Note that this v is for the accelerating potential and this v is for the velocity. Now, the energy of an electromagnetic wave, as we have seen it in our previous topic, that is electromagnetic spectrum, the energy is given by hf, where h is the Planck's constant and it is given by this value, 6.63 times 10 to the negative 34 joules second, and f is the frequency. So in other words, we can be able to get the energy of the X-rays produced, because X-ray is part of electromagnetic spectrum. It is an electromagnetic wave. Therefore, the energy that is converted to X-ray, we can be able to get it through this formula. The highest frequency of X-ray is released, or the highest frequency of X-rays released after an electron hits the target is when the minimum kinetic energy is lost in form of heat. So in other words, we are saying that when the most of kinetic energy is converted to X-rays, then we will get X-rays of high frequency. That is, HF max is equals to EV, where E is our electron charge and its value is 1.6 times 10 to the negative 19 coulombs. Then the lowest frequency is released when the electrons make multiple collisions, losing energy in stages. Remember, we have said that that tube must be highly evacuated, but sometimes you may find that there are particles that were left. Therefore, if the electrons keep on colliding with those particles, they will lose energy, And when they reach the target, they will have minimum kinetic energy, and therefore whatever you will get X-rays of lower frequencies. Now, for you to get the minimum wavelength, we proceed as follows. We have that electron volt, that is the energy or electrical energy, is given by the energy of the wave HF, but we know that C is equals to lambda frequency, so our F will be C of a lambda. So instead of writing F here, we write C of a lambda. We have just replaced F, which implies that if we make our lambda minimum the subject of the formula, we'll get that it is Hc of a EV. So that way you're able to get the wavelength of the X-ray produced. Now this expression that we have seen here can be used to calculate the energy, the frequencies, and the wavelength of the X-rays. We look at the first example. Determine the energy possessed by X-ray whose frequency is this one. Now for you to get the energy, we are using the energy of electromagnetic wave. That is E is equals to HF, where H is the Planck's constant. This is 6.63 times 10 to the power negative 34 multiplied by this. Now when you are multiplying using your calculators, make sure that you put the bracket in our first term, and then you multiply again putting the bracket in our second term. And when you do that, then you're able to get this value. That is 1.989 times 10 to the power negative 16 joules. We move to our second example. We have that an X-ray tube operates at 60 kilovolts and the current through it is 4.0 milliamperes. Calculate the number of electrons striking the target per second, and number 2, the speed of electrons when they hit the target. We proceed as follows. The current through the tube is given by I is equals to Q over T. We know that the current is rate of flow of charges. So it is always given by the amount of charge divided by T. But how do we get our Q here? That is, how do we get the amount of charge in this tube? The amount of charge is given by NE, that is the number of electrons multiplied by the electron or the charge per electron. The number of electron multiplied by the charge per electron. Then we divide by T. That way we are able to get the current. But we have seen that we are calculating per second, the number of electrons striking the target per second. So our T is equals to 1 second, which implies that our equation or our formula here reduces to I is equals to NE. So from there, we can be able to get N. N will be equals to I divided by E, where I is the current and E is the electron charge. So when you put them in your calculator, again, put the bracket, this one, and then you divide again, you put this under the bracket, then you divide, you will get that the value will be 2.5 times 10 to the power 16 electrons. Then number 2, you're supposed to get the speed. But before you get the speed, you need to get the kinetic energy. Our kinetic energy is given by a half mv squared is equals to EV. So we can make V the subject of the formula. It will be the square root of 2EV divided by the mass of electron. When you substitute the values, again putting brackets in each case and then dividing, you will get that the value is 1.45 times 10 to the power 8 meters per second. Then we move to another example. A potential difference of 30 kilovolts is applied across an X-ray tube. Given that the charge of an electron is this one and the mass of electron is this one, calculate the kinetic energy of the electron. Now to get the kinetic energy of electron, we always get the electron energy, which is EV. And EV is the electron charge multiplied by the potential difference. When you multiply, you get that it is 4.8 times 10 to the power 15 joules. Then we have example 4. The energy of X-ray is given as this value. Given that the speed of light is this one and the Planck's constant is this one, find the wavelength of the X-ray. So again, we start with our formula. E is equals to HF. But for an electromagnetic wave, we know that C is equals to lambda frequency. So from there, we can say that F is equals to C of a lambda. Then we substitute. we get that energy is equals to hc over lambda. We have done it earlier. So again, we make lambda the subject of the formula. So our lambda will be hc over energy. And the energy is given here. So again, you put the values. This is the Planck's constant, 6.6 times 10 to the power negative 34. Then this one is the speed of light. This one that is given 3.0 times 10 to the power 8. After that, put the bracket, multiply the numerator, then divide, put the bracket, insert the denominator, and you'll get this value, 9.955 times 10 to the power negative 12 meters. That is our wavelength of the X-ray produced. From there, we have the assignment. These assignments are testing what we have just covered. So make sure that you revise, you teach the others, you practice before you come to the assignment. Thank you, and let us meet in our next lesson.